All right, good morning, everybody. Can you all hear me? Can you see me too?
Yeah.
Okay, let me turn up the sound to my computer real quick. All right. Just a couple of changes to your assignments. Your chapter 24 homework is due on the 28th. Proposition charge due on the 25th. And for this week, you want to read through 24 and 25. You don't need to read all of 25, but we're going to get about maybe halfway through chapter 25. And then there are some conceptual questions. Every unit, well, the next 3 units have a set of conceptual questions that you can use to practice with. You can practice on your, just to practice to get ready for the exams. And you can look at them now. You can try to answer them as you're reading through the book or as you're going through the homework. The key is, in one of the modules, I kind of hit the key in one of the modules just because I really want you to I want you to practice by doing the conceptual questions, try them out, and then look at the answer and try to understand why that's the correct answer. Okay? But every unit, the next 3 units have a set of conceptual questions there for you to practice on so that you can get ready for the exams. Okay? So take advantage of them. Use them. Okay? Today what we're going to do is do some calculations involving Gauss's law. We'll talk about the electrical potential and electrical potential energy. But a couple of things before I get started. Number 1, properties of the charge lab. Do you have any questions regarding the properties of the charge lab? Please don't wait till Sunday night to do the lab or Friday night to do the lab, okay? Because that won't work out. It's a much longer lab. Yeah, the details are in the lab itself. So when you go into Canvas and you look at the file for the lab, it'll say, try this. So part 1, there's 3 different phenomena you can play around with. Okay, your mic isn't working, sorry. Are you, let's make sure you're not muted. There's 3 different phenomenon in part 1, and you just gotta film one of them, okay? Okay, sorry about that. Yeah, just go ahead and type in the chat then. And you just got to film one of them. And then part 2 and 3, you just got to film, just go through every step in parts 2 and 3. They should be fairly straightforward. If you're not understanding something, just feel free to email me. And I'll try to answer the question as best I can. Okay, but typically the instructions are fairly straightforward. So I have a family commitment this week. I'm going to be out of town Thursday and Friday. So Professor Shakel, she's going to be handling the lab meeting this Friday. And she will be answering questions on the multimeter quiz. Okay? So any questions you have on the multimeter quiz, you should ask her. So, and I know you're working, it makes you work on 2 different labs, but the multimeter quiz is not very long. There's a simulation on the modules for the multimeter quiz. You should play with it a little bit before you come to lab on Friday. That gives you an idea of what the multimeter quiz is going to be like. And I know the multimeter quiz is not due until October 3rd, but you should play around with the multimeter, how to use it, and any questions you may have, you will ask, please ask Professor Shakel, okay? So she's only going to be there to answer questions on the multimeter quiz. So if people don't show up within the first 10 minutes, the class will be over, okay? So make sure you show up and ask questions on the multimeter quiz. Properties of Charge Lab, try to email me. I'll try the best I can. Like I said, I will be in an airplane on Thursday. Most of the day I'm flying to the East Coast. So I'll try the best I can. When I get there, I'll respond, okay? And then Friday, when I can respond to your email, I'll respond to your email. And then Sunday evening, I'll be in a plane back. All right. Any other questions? Properties of Charge Lab, concerns?
Hey, quick question. The student help hours for Thursday probably won't be held because you'll be away.
Yeah, unfortunately, I cannot hold them on Thursday.
Yeah, no worries. Just checking.
Yeah. Yeah, I wish I could. But, I mean, if something happens where I could do it, I'll give you an announcement, but I doubt I can because I think that's about the time when I arrive on the East Coast, something like that. So it might be a little bit difficult for me.
Yeah, no worries. Thank you.
Okay. And I'm going to try to upload so every time I change the deadlines on WebAssign, I have to actually upload all the assignments back into Canvas so that on Canvas the dates are correct. I'm going to try to do that within the next couple of days. So, because some students have been expressing confusion, and I know some students don't like that, and I'm trying to avoid confusion as much as possible. So, the main thing is with Chapter 27. And I apologize for the issue with 27. Okay. I will assign Chapter 27 when we cover the next unit. It's a short assignment, okay? But don't worry about it until that. But you should kind of scan through it because you have a lab on it, okay? Any other questions? Well, I'm going to do something a little bit different today. I want to ask you some questions. Okay? I have some questions to ask you. So I've set up a poll in Zoom. Let me find it. And I really made it very generic. So I set up a poll for, and I have about 4 or 5 questions to ask you. I want to just see where you're at. Okay, I just want to see where you're at. So I'm going to launch the poll. Do you see the poll right now?
Yeah, I see it.
Okay, so I'm going to switch windows so you can see the entire slide for the question. So my first question, and you only answer choice 1 or choice 2. I just made one poll question. And then this one's going to show up for every single question that I'm going to ask. So choose your response to this question. And granted, there's only 4 people here, so I hope the other folks watch this video. So I guess this poll will go pretty quick since there's only 4 of you. Okay, so 4 people responded. Let me end the poll. Oh, by the way, it's an anonymous poll, okay? So let me share the results. You folks see the results?
Yeah, we see them.
Okay, so it's 50-50. Let me stop sharing. Okay, so when we talked about the properties of the Charge Lab, I did a demo with a 2x4. Right, this is the 2x4. And I took a rod that was charged and brought it near the 2x4. Okay? And what happened to the charge in the 2x4? Well, the electrons in the 2x4 don't like the electrons here, and so they would move away as far as possible, leaving a net positive charge on the surface closest to the conductor, to the negatively charged rod. And when they did that, the 2x4 was attracted to the charged rod. And the 2x4 was uncharged. Okay? No matter what the materials are, the uncharged object will always be attracted to a charged object. Okay? An uncharged object is always attracted to a charged object. So for the answer to the first one was true. It's always the case.
Is this similar to like what we're doing in this lab with like the pieces of paper and showing that those are like attracted to the electrophorus because the electrophorus is charged?
Correct.
Okay.
Yeah, and even in the first part, when you do the charged rod with, for example, salt or sugar, same thing. That stuff's not charged, and you're able to pick that up. If you take a balloon and rub it on your head, and then take the balloon and put it on the wall, it will stick to the wall, and the wall is uncharged. So this is always so it's always true that a charged object will always be attracted to an uncharged object, and vice versa. Okay. All right. And by the way, the uncharged object can also be a metal, and if it's a metal, the effect is actually stronger. If this was a metal rod, the effect would be stronger because the electrons are free to move in the metal rod. All right, let me go ask you another question. So this one, oh, hold on a second, let me try to start the poll. Okay, so this one is more of a setting up the integral to do the calculation. So you want to calculate the electric field due to that small portion of the rod. You want your dE for that small portion of the rod. So you want to quickly set up the expression for determining dE for that small portion of the rod at point P. So go ahead and make your choices. I'm going to draw, as you're choosing, I'm going to try to draw a picture of the system on the board. Okay, let's take a look. Excuse me. Okay, so everyone's responded. So let me end the poll. Let me share the results. So we have a nice distribution of responses. Okay, so the majority of students picked choice 2. Let me stop sharing. Excuse me. Okay, So I want to find a dE as a result of this. This rod is uniformly charged. Sorry. So my dq is lambda dx. And since this is uniformly charged, this is Q over L. Okay. My R squared is just this distance squared. Now my R hat, if this is theta, it's cosine theta I hat plus sine of theta j hat. But it just wants the y component of the field. It only wants the y components. So sine of theta is opposite of our hypotenuse. So then dE, at least the y component, because that's what it's asking for, is going to be k dq. dq is q over L dx over r squared times the sine of theta. So that's the answer. And so that one was A. Questions on that? Okay, I have another one. This one's a little bit harder. Let me relaunch the poll. So now I have a ring of charge with the charge density that's given, and you want to know which is correct regarding the field at the center of the ring of charge. Make sure you draw a picture as you're sitting, or wherever you're sitting. Draw a picture of the system. And lambda naught's lambda naught just a constant, some number. If you want to make it 1, you can. You don't have to set up your dE to do this. You just have to think about what the contribution of each ds is to the total field. All right, so I got one more person who needs to respond. All right, so we have one person choosing A, another person choosing B, another one choosing C, and another one choosing D. A nice distribution of answers. Okay, all right, let me stop the sharing. And So what I'm going to do, I'm going to go in all four quadrants. I'm going to take a little piece of this arc. I'm going to take a little piece of this circle, this little arc length ds. Let's pretend that lambda naught's positive, so that makes this whole thing positively charged. And so that means the field is going to point towards the center, at least relative to this guy, because the electric field always points away from a positive charge. Like that. So let me go on the opposite side, about the same angle, and draw another ds. This length is supposed to be the same as this length. It's a ds. And of course, the field is going to point towards the center. And I can do this here. And on the opposite side here, for example. Okay, and granted, they all point towards the center. But there's something I didn't draw correct in my picture. What didn't I draw correctly? Well, the length of the vectors that represent the fields are not drawn correctly. If lambda equals lambda naught e to the minus theta, where theta is measured counterclockwise from the positive x-axis, how big is this charge as compared to this charge? This angle's smaller, so e to the minus theta is bigger than this one. So this arrow is going to be longer than this one going in the opposite direction. In fact, it's going to be significantly longer. Okay? These two arrows that point in the opposite direction, they're going to be smaller because the angle's big. In fact, this is going to be the smallest arrow because the angle's so big. This is going to be by far the biggest arrow. Anything close to 0 is going to have the longest arrow. Okay? So this term is going to dominate. And as you go this way, the arrows get shorter and shorter. So what does that say? It says that the field has to be somewhere in this direction. Which quadrant is this vector? The total field is going to be somewhere like this. Which quadrant is that in? Isn't that the third quadrant? I know I drew this arrow in the first quadrant, but it's pointed towards the third quadrant. Okay? So the field is going to be somewhere in the third quadrant. It's not going to be 0, and the reason why it's not going to be 0 is because this decays exponentially. You can actually solve this problem because the integral is not that difficult. Okay? All right, let's try a couple more. Now we're doing field lines. They got two, this one and another poll question. So the red arrows indicate the electric field lines. What can you say about the net charge inside the box? Look at the number of field lines going into the box, number of field lines coming out of the box. You can't see inside the box though. Okay, so let me end the poll and share the results. Let me stop the share. Okay. So when you look at that picture, in fact, I'm not going to draw anything on the board. Let me go back to the picture. If you look at the left-hand side of the box, you have less field lines going in the left-hand side of the box than the right-hand side of the box. You have less going in than coming out. So you have more field lines coming out of the box. And that one we know, okay? We have a net positive flow out of the box. Right? Because you only have, let's say, 3 lines going into the box, but like double that going out of the box on the right-hand side. And that represents this integral. That integral is equal to the total charge enclosed over epsilon naught. And if you have a net flow out of the box, which we have here, and n is, remember n is directed outside out of the box, that means we have a positive charge. So for this one, the answer is A. It's a positive charge. Okay, that's indicative that you have a positive charge. Okay, or at least a net positive charge. Okay, that's really what I should say, is that you have a net positive charge going out of the box. All right, let's try one more. And all right, so this time we want to look at the flux through the box. In fact, it's just the flux through the front surface of the box. Okay. And the electric field is uniform on the front surface of the box. It's 10 newtons per coulomb, but it's directed at 30 degrees with respect to the normal to the front of the box. Okay, I got everyone's responses. Let me end the poll, Share the results. Okay. Let me stop the share and let me end the poll. Okay. What we're calculating is this integral when you're finding the flux. It's on the open surface. Oops, I forgot that one. For open surface, let me check the. Oh, I thought I showed it. I'm sorry. Let me see if I can show it again. See it? So most people chose choice 4 or D. Okay. So we want to calculate this. Now the electric field is uniform. In fact, the dot product between E and the normal to the surface is the same all the way around the front surface. So this thing is a constant over the whole surface, which means that I can pull a constant out of the integral sign. And integrate over the area of the front side of the box. Well, the front side of the box is 2 by 2. So 2 times 2 is 4. So now I just got to figure out what the dot product is between these two. The dot product is the magnitude of the first vector, which is 10 newtons per coulomb, the magnitude of the unit vector n, and then the cosine of the angle between the two vectors. So if I have a unit vector like this, and the other one is, the way you see it there, that angle is not correct. You got to put the vectors tail to tail to actually get the angle between them. If you put them tail to tail, the angle's this. The angle between two vectors is always defined when you put the two vectors tail to tail. And so this is cosine of 150 times 4. 10 times cosine of 150. This is root 3 over 2. It's like 0.87. So this is 8.7 times 4. Actually, I'm sorry, cosine of 150 is negative root 3 over 2. And so this is about minus 35 Newton per coulomb meter squared. So that angle between the two vectors, you got to think about it. You got to put the two vectors tail to tail to measure that angle. So that's a little bit deceiving in that picture. Okay. They're almost 180 degrees apart, in fact. Where that means the dot product would be negative 1. Or I'm sorry, the cosine of 180 is going to be negative 1. Any questions on that? Okay, so I wanted to do a polling question so that not only would I could see where you're at, but you can see where you're at in terms of understanding this material. But I'm hoping that what you're doing right now is try to do maybe about 3 problems a night on chapter 24. If you do all the problems in the homework at once, it's going to make it hard for you to learn the material. I highly recommend when students take a physics class, they try to do about 3 problems a night, if they can. Then you see the material over and over again, and the material will sink in. So I did forget to ask you guys, this is not a polling question. I did forget to ask you guys this question last week, and I wanted to ask you because it has to do with the properties of charge lab. Okay, my last question for the day for you guys. Okay, I know I'm spending a lot of time on questions, but I think it's important for you to assess where you're at. So a student does an experiment and has 5 styrofoam balls. They're suspended from insulating threads, and experiment was performed with the following results. Ball A attracts ball B and repels ball C. Ball D attracts B and has no effect on E. A negatively charged rod attracts both A and E. And we'll only answer the first question. What is the charge on each ball? In other words, I want you to tell me what is the sign of the charge on each ball. So think about it for a minute. I want to know your answers. I want you to tell me, either in the chat or just blurt it out. What is the size of the sign of the charge on each ball? What do you think? Oh, I'm sorry, I didn't see the question in the chat. Sorry about that, Scott. And thanks for answering it, Ryan. So, what is the charge in A? Tell me. What do you think it is? Is it positive, negative, or uncharged? Those are the choices. Okay, let's see. A is positive. Let me write this down. And we can argue if we want about it. A is positive. The monitor's too far away. B is negative. C is positive. D is negative, and E is neutral. Everybody agree? Did I get that right? Positive, negative. Okay. So everyone's agreeing. So let's test this out. Okay. So if A and B are positive, they will repel each other, which makes sense. I'm sorry. If A and C are positive, they'll repel each other. A and B are oppositely charged. They will attract each other. That makes sense. Now, ball D attracts B. Or is that what it said? Ball D attracts B. Oh. Okay, so something's wrong here then, right? What do we have to change? D would be positive? Okay, so let's change that to positive. So now these two attract each other, which makes sense. But then it says ball D has no effect. Right? Ball D has no effect on E. Remember what we said earlier. The first question I asked you today, a charged object is always attracted to an uncharged object. It says ball D has no effect on E. Okay? That's not what this says, right? This says that they're attracted to each other. Whether I make this positive or negative, these two would be attracted to each other. So what must D be? D must be uncharged. Now, if you go through this combination, it'll work. A negatively charged rod attracts both A and E, which is true because a charged object will always be attracted to an uncharged object. Yeah, right, Scott. I mean, that's the first question I asked today, right? The question with the problem with the 2x4. It will. D will be attracted to the rod if it's negatively charged. Isn't that what happened with the 2x4? And D will be attracted to the rod. But it doesn't say anything about D and the rod, though. It just says about D and E. D has no effect on E. So if I bring these two together, they won't attract each other. Yeah. I mean, my first question was about, that's why I asked that first question, because an uncharged object and a charged object will always attract each other. And the sign of the charge on the charged object doesn't matter. Okay? Like you do part one in the lab, you take a negatively charged rod and you bring it near something that's neutral, they'll always attract each other. Okay? All right. So this is the answer. Just go through the logic of it and you'll see that it'll work out in every case in that problem. All right, so what we're going to do now is then continue our discussion in Gauss's law. I know I took up some time, but I wanted to go over this just so that we see where we stand. I'm going to try to do this every once in a while in lieu of giving a quiz, I guess. Oops, sorry about that. Okay, so what I want to do now is go back and discuss Gauss's law and use Gauss's law to calculate electric fields. Remember last time we left off, and unfortunately it was a week ago, we talked about this expression. This is Gauss's law. It is one of the important equations in Physics 210. It's one of Maxwell's equations. Maxwell's equations summarize everything about fields in this course. Okay? So we want to use this to calculate fields. And remember that this represents the number of field lines going outward from a surface. If the integral is positive, it represents the number of field lines moving outward from a surface. But this is also proportional to the amount of charge enclosed inside the surface. So I had a whole discussion on this last week. And we can use this idea to calculate electric fields. Not in every case. I mean, this is always true. In fact, this is true whether or not the electric field is time dependent or not. This is true whether the field is uniform or not. However, I can use it to calculate the electric field only in special cases. And the special case I'm talking about is the case where I can pull the term in parentheses out of the integral. If I find a case where I can do this, then I can solve for E. Well, I do need to know this is the angle between these two. Okay, I do need to know the angle between these two vectors. And then I can solve for E. And there are certain conditions for which we can do this. So let me list the conditions that will allow us to be able to use Gauss's law to calculate fields. Number one, the electric field has to be symmetric over whatever imaginary surface we draw. I shouldn't say symmetric. It must be uniform over the surface that we draw. I'll give you an example. If I have a point charge and I draw a square around it, or box around it, the electric field looks like this. Since the distance from here to here is greater than the distance from here to here, the electric field anywhere here is going to be different. Not only that, this angle between these two vectors changes anywhere on the surface of the box. So if I drew an imaginary box, just a box like that, that box would be useless for me to be able to calculate my electric field. However, if I drew a sphere, that's different. If I draw a sphere around that charge, let's say I put the charge at the center of the sphere, then the distance from the charge to from the center of the sphere, where the charge is located, to the surface of the sphere is the same. That means electric field is the same all the way around here. And the angle between the electric field and the normal to the surface is also the same. So then I can pull the E dot n out of the integral. And I can use then this surface that I've drawn to actually calculate the electric field due to the point charge. I don't have to use kq over r squared. In fact, I would end up deriving kq over r squared using this idea. So this dot product, the angle between these two vectors, if we want to use this to calculate electric field, should be either 0 or 180 degrees. In other words, the dot product, remember the definition of the dot product, is the magnitude of the first vector times the magnitude of the second vector. Of course, this is 1 because it's a unit vector. And then times the cosine of the angle between them. So this angle is going to be either 0 or 180. So for the case where the angles are 0 or 180, then this is nice. I can pull this out of the integral sign. In the other cases, you're not going to have enough symmetry. If the angle's 30 degrees, that angle is not going to be 30 degrees over the whole surface. Okay. But if it's 0 and 180, 0 or 180, it's possible to have that value over 0 or 180 over the whole surface. Okay. So the electric field basically has to be parallel or anti-parallel to the normal to the surface. Or another thing, you can argue that maybe the electric field is 0 over the surface. I'm going to skip this video just because I shouldn't be playing it if I'm going to put my video on YouTube. So now we're going to do some examples where I just calculate the electric field. And I have several of them. So chapter 24 is pretty much all about this equation. Sometimes Q is written this way. Okay, and I know that most people are not going to feel comfortable with this equation in this chapter. And usually it's not until you've seen this material a second time, like at a junior level, that you might start feeling comfortable with this material. I understand that. That happened to me too. Okay? But we still got to learn this stuff. All right? So suppose I have a uniformly charged insulator. Not a conductor, an insulator. So that's an insulating sphere. Okay, I know I didn't draw it very well. Okay. I want to use Gauss's law to calculate the electric field inside this thing and outside. Here's the caveat in doing this problem. This is an isolated system. There's no other charges around it. Okay? There's nothing around it. So the total charge on this thing is Q. And there's nothing around it. So, and the radius of this thing is B. I want to determine the electric field inside it. So I am going to use some physical reasoning to get my answer, okay? And I'm going to use Gauss's law. Okay, so the big thing here is this is an isolated system. There's no charges around it. So I'm going to apply Gauss's law inside my sphere. So this is a real sphere that's charged. And I know that it's going to produce an electric field that looks like this. Because of its symmetry. You guys probably make a better picture than I can. Okay? Positively charged, the field line points away from the sphere. It basically has the same, because of its symmetry, it has the same behavior of a point charge when you're outside the sphere. But I want to find the field inside. And so I'm going to draw an imaginary surface. Let me draw it in blue. So the blue is imaginary surface. And the red thing is a real thing. I want to apply this inside the surface. Okay. I'll take the integral. V dot n dA equals Q over epsilon naught. What's Q inside? How much charge is inside the sphere? None. All the charge is on the surface of the sphere. So this is equal to 0 in this case. So that integral is equal to 0. Well, if that integral is equal to 0, and there's no charge anywhere other than this thing, then what must the electric field be inside? You did, and I'm sure you did a problem like this for gravity, although you didn't use Gauss's law. If there's no charge anywhere in my universe on the board, okay, and this integral ends up being 0, what must this be? It's got to be 0. Yeah, it's 0. So the field inside's got to be 0. If I had a charge over here, outside it, then what I have done is not sufficient for me to figure out what the field is inside there, because I haven't taken into account this thing. I would have to use another surface, Gaussian surface, to actually try to figure out what the field is over there. Okay. Okay, so E equals 0 for all distances less than or equal to B. Right? For any R, for any Gaussian surface of radius R that's less than B, that integral is going to be 0. There's no field inside. So inside there's no field. So now let's draw outside. We go outside it. And so this integral is not 0 anymore. It's Q over epsilon naught. This thing acts like a point charge. The electric field points outward. The normal to the blue thing is parallel to the electric field. And the electric field all the way around this sphere has got to be the same value because of symmetry. Because you're always the same distance away, right? The distance is always the same. But it's the same value. That means then I can pull the E out of the integral sign. In fact, I can put an E dot N out of the integral sign. But these two are always parallel all the way around, so this dot product is just E. Because you're taking the dot product of a number and 1. And then I integrate over dA. And this distance now, we're talking about a radius of R. So what's the surface area of this sphere? Because that's my dA. What's the surface area of this sphere? Well, it's going to be, I'm going to get E times 4 pi R squared. Now I solve for E. But 1 over 4 pi epsilon naught is K. Should be less than B, not less than or equal to, sorry. It's a field due to a point charge. If I were to graph the electric field, as a function of how far away you are from the center of the sphere, inside it's 0. Then it jumps up like this, and then it depends on 1 over R squared. That's what the field looks like. Okay? It's like that of a point charge. If you do the point charge, you get the same answer. Are we okay with that? Now let's do a solid sphere. I want to do the solid sphere inside and out. This one's going to be a little more work. But this is going to have the same symmetry as the previous problem, so I'm going to choose spheres. Why did I choose spheres for my imaginary surface? Well, because it has the same symmetry as the spherical shell that we just did. I cannot use a box, because then I won't be able to pull the E dot dn out of the integral. By the way, one more thing I forgot to mention. Gauss's law only allows you, I'm sorry, go ahead. Do you have a question, Ryan? Oh. Gauss's law only allows you to calculate the magnitude of the field. You have to use a little bit of intuition to figure out the direction. If the charge is positive, it points away from the sphere. If the charge is negative, it points towards the sphere. Okay. So we're calculating field strengths. And really that question that you see in the slide should say, what is the electric field strength? Although we can figure out the electric field because of the fact that it's either going to point towards the sphere or away from the sphere. But okay. So now we have a solid sphere. Again, it's an insulator. Conductors are a little bit different. Conductors are special. Okay, we're going to say something about conductors. So let me draw a solid sphere. Okay. So there's my solid sphere. I want to find the field everywhere inside and outside the solid sphere. And this sphere has a radius r. Big R. Let's figure out the field inside. And so what I'm going to do is I'm going to draw an imaginary surface, the same shape as the sphere. So that's my imaginary surface. Hold on a second. I guess spell. Of radius r. Some arbitrary radius r, okay? We're given that the charge density is not uniform. This will help you. This is hopefully to help also with problem number 9 of the previous homework assignment. Because I know some people had questions. By the way, it's very hard to answer that question via email, unfortunately, for problem number 9. So rho is equal to some constant A divided by R. So what that means is, as you go further and further away, the charge density decreases. The charge density is maximum at the middle. Okay. So this whole thing is charged. So I have some charge inside this thing. And what I have to do is figure out how much charge is inside my purple sphere. Okay? I just got to figure out how much charge is inside my imaginary purple sphere. I know that the electric field is going to point outward like this because of the symmetry and because of the fact that the charge density only depends on ours. It's going to depend radially. The electric field's like that, but then the normal to the surface is parallel. So this dot product is going to be E times 1 times cosine of 0. Of course, if this was negatively charged, then it would be E times 1 times cosine of 180. So I'm going to set up this integral. But this is what's enclosed inside this thing. In order for me to figure out what's enclosed in here, I have to integrate this thing from 0 to r. Hold on a second, I did that badly. Okay. Well, let's focus on the left-hand side. I can pull this dot product out because E is uniform over the purple sphere. I'll work on this later. This dot product is just going to give me E because these two vectors are parallel to each other, and E is the same value all the way around the surface. N is 1. The unit vector is a vector of length 1. This is going to be the surface area of this little sphere of radius r. So now I got to figure out what this integral turns out to be. Okay, I want to figure out what this integral ends up being. So if I have a sphere, how do I break up a sphere? How do you break up a sphere? Well, if the density only depends on r, then I can break up the sphere in terms of a bunch of shells, like an onion. Yeah, quadrants, you can do rings. Yeah, and you can do rings. The problem with doing rings, because you have to not only integrate around the ring, but then you have to integrate around all the rings. So you still have to do at least 2 integrals. I want to do 1 integral. What if I break it up into shells? Of course, you can also do a 3D. You can also do a triple integral for a sphere, but I don't want to do that. Right? Just imagine breaking up a shell into a bunch of, I'm sorry, not a shell, a sphere into a bunch of thin shells. Imagine cutting through an onion. What does the onion look like? The onion is basically a bunch of spherical shells with a thickness. And if you add the volume of all the onions together, all the layers of the onions together, you get the total volume of the onion. And so what I'm going to do is I'm going to break this up into shells. Of thickness dr. The surface area is 4 pi r squared. And so my element of volume is 4 pi r squared dr. And what if you integrate that? What do you get? Don't you get 4/3 pi r cubed? If you integrate that, you get 4/3 pi r cubed, which is the volume of a sphere. So I'm going to get 1 over epsilon naught times my density And I'm going to integrate from 0 to whatever this surface of my imaginary sphere is. And I have a problem right now. Your math professor would say I have a problem right now. You know what it is? I have an R here and an R here, which makes the notation very, very bad. Okay, the math instructor would say I have bad notation. And so what I should do is rewrite these in like R primes. I call them dummy variables. Okay, I would call these R primes. They're called dummy variables. And so then what I would do is not, perform the integral. So I got to find my eraser. I don't know where I put my eraser at. Okay, so I'm going to have E times 4 pi r squared equals 1 over epsilon naught. Oh, I can pull out the 4 pi a here. Let's see, r squared over r Oh, that's not a tough integral, right? Because if I integrate this, I just get r squared. This 4 pi and this 4 pi cancel. Wow, this r squared and this r squared cancel. So E ends up being a over epsilon over 2 epsilon naught. What does that mean? Well, that's a constant, that's a constant, that's a constant. The field inside's constant. By the way, any of these problems, if you want to check if your answer is right, the field inside is going to be 1 power higher than the density. Okay? The field inside will always be 1 power higher than the density. Which is r and which is r prime. R prime, I made a dummy variable. The r is my radius of my imaginary sphere. I put r primes here just so I can make this look different from this. You don't want to make this the same as this. That's bad practice. So I just call these arbitrary, or they're just arbitrary. Okay? Just so that the notation doesn't get confusing. Yeah, because you have an r prime squared here and an r prime there, right? R prime squared over r prime is r. Okay. So the field inside is uniform, but now we got to do the field outside. Okay? So if I do the field outside, now I got to draw an imaginary surface. I don't want to redraw this because I only have one board too. I'm going to draw an imaginary surface like this. And realistically, everything is almost the same. If I go outside the surface, this is the same. I mean, this dot product here is going to be the same. This is the same. Now something changes here. What do I integrate to? Now, this sphere is a radius r. What do I integrate this to now? Like, I don't need these dummy variables in this case. What are my limits of integration? It's not r to infinity, right? Because I want to know how much charge is enclosed inside my big purple sphere. Right? This time my purple sphere is bigger than the radius of the sphere. My imaginary sphere is bigger. So well, it's not r to r because I'm integrating this integral represents the charge. So I got to integrate from here to here. So I include all the charge. Remember, this integral represents how much charge is enclosed within the Gaussian surface. And so this has to go from 0 to the surface of the sphere. There's no charge here. There's no charge in between these two spheres, and there's no charge afterwards. Because remember, this integral represents the charge enclosed inside my Gaussian surface. So I got to include the whole sphere. All right, now I'm integrating over the whole sphere. And of course, this is not going to be hard. Change this to big R. I don't need my dummy variables anymore. And this becomes big R squared. And then I'll have a big R squared here and a little r squared here. So let me rewrite that because it's not that clear. The electric field is going to be A times r squared over 2 epsilon naught little r squared. So the field depends on 1 over r squared. If you knew the total charge and you solved for whatever A was, you would end up getting kq over r squared. If I plot the field inside, or inside and outside, I get the following. You get a constant, and then it goes like this. In fact, let me write the expression. So E is equal to A over 2 epsilon naught for r less than or equal to big R. And E is A r squared over 2 epsilon naught little r squared for r greater than or equal to r. And notice if little r equal big R, you get this. Okay? That's what you get. Now, what if you have something that's linear? What if the density was, not linear. What if the density was constant? If the density was constant, the electric field would look like this. If you took Physics 205, you did this problem for gravity. I know you did. Okay? That would be the field inside the Earth. The gravitational field inside the Earth would look like this. So if the density is like this, then the field's constant. If the density is a constant, then it's linear. And so you can tell if your answer is right, because when you look at the field inside is going to be 1 power higher than the density. Why is that? Because charge depends on r cubed, and the field depends on 1 over r squared. That's why. All right. Let me do one more, and then we'll take a break. Okay, let me do one more, and we'll take a break. We'll take a 20-minute break, because this next one is not a long one. And these examples are in your book, and you actually have to go over and over and over again, really, before it starts sinking. I know this is hard stuff. I understand that. Just got to hang in there. We get through it. People have gotten through this for many years. You'll get through it. And that's why I've created a worksheet for this. So your properties of charge worksheet is due on the 30th. Gauss's law worksheet is due on the 30th. Okay. That's supposed to help you with this understanding Gauss's law. Okay. So let's do this one other example, and then we'll take a break. Now I have a line of charge. And let's pretend it's really long. Let's pretend we have a long wire, essentially infinitely long, with charge density lambda. Okay. I know the electric field due to this thing is going to look like this. Think of a line of charge as being a bunch of point charges stuck together. Try to draw field lines of a bunch of point charges stuck together. You're just going to get something like this. Okay? So let's draw the field lines. And so I want to find the field due to this. Now, I cannot do this for a wire that's not long, because what happens if I have a wire that's not long, I'm not going to have the symmetry I need to use Gauss's law. Because weird stuff happens at the edges. The field lines actually bend at the edges, so I lose my symmetry. So I got to make this, I'm going to pretend it's infinitely long. And you might say, well, there's no such thing as infinitely long wires. But I'll give you an example where this approximation will work. Okay? Am I going to use a sphere to do this? Am I going to draw an imaginary sphere to do this problem? I mean, imagine if I drew a sphere, this dot product would not be constant over the sphere because these point straight upward. What shape should I choose for an imaginary surface? What shape should I choose? What would be the wise choice? Yeah, I use a hollow cylinder. That's what the picture shows you, right? So I'm going to pick a hollow cylinder. Why? Because imagine these field lines go all the way around the wire, right? If I pick a hollow cylinder, the normal to the surface of the cylinder points like this. So what can you say about that dot product along the surface of that cylinder, the lateral surface? I mean, that dot product is going to be constant all the way around. Well, what about the ends? What about the flat parts? Well, there's no field on the flat parts. There's no field going here. Right? There's no field going this way. There's no field going that way. So that dot product will be zero. If this was not infinitely long, that dot product would not be zero on the flat parts. And it would be something complicated. So my surface area is basically the lateral surface of my cylinder. And so now I apply this thing. Again, I can pull this out of the integral. But I have to integrate over this thing here. It's going to be dx, sorry. I got to integrate from 0 to L. You may say, well, L is infinite. Yeah, don't worry about that. I know L is infinite, but something nice will happen. Okay, you'll see. E dot n is just going to be E because the E, no matter how big this thing is, the dot product will still be the same. So I'm going to get E times the integral of dA. This integral is lambda times L. You might say, that's infinite. There's something wrong there, man. I'll say, yeah, don't worry about it, okay? What's the lateral surface area of that sphere? I'm sorry, that cylinder. It's 2 pi RL. What happens to my L's? They cancel. And so I get E times 2 pi R equals lambda over epsilon naught. And so the magnitude of the electric field, that's why I'm not putting a arrow, I'm not putting a arrow over it because it's the magnitude, is going to be lambda over 2 pi R epsilon naught. Or you can write it as K times lambda over 2R. Oh, no, I'm sorry. 2K lambda over R. Okay? And you're going to say, well, there's no such thing as an infinitely long rod, and you're right. Suppose I wanted to find the electric field due to a rod, uniformly charged, and I'm real close. If you're real close to the rod, how long does that rod look? How long does the rod look if you're real close to it? Doesn't it look like it goes on forever? Yeah. And so, as a result, if I want to find a field real close to the rod, I can use this approximation, and it'll work really well. The closer I get, the better the approximation. And this is way faster than setting up the integral. So if you're real close, you're going to be over 95% accurate. And that, for most applications, is probably good enough. Okay. All right, I'm going to do one more example after lunch, and then, or after our break. It'll be my lunch. Okay. And then we'll talk about conductors and equilibrium. And we've talked about, you know about equilibrium already, but this is just a special case. Okay, so let's take a break, and we will meet in about 20 minutes. So maybe 12:52. Okay, 12:52, 12:53, around there. We'll meet again. So let me stop recording.